Find the long run behavior of this function. So I want to let you know that you can just graph that function to find the long run behavior. So I've graphed it for you. And just click on, so here is the equation. If you are going to go ahead and graph it, do make sure to put the numerator in parentheses and the denominator in parentheses. So I've graphed it here and I click here and then look, that's what we get. So you can visually observe. We said the answer here, let me just review. We said the answer here was a -1/5. And as we go to positive and negative infinity. So let's look at the graph and just verify that in the graph. So as I click on points here, and as we kind of go, keep going, so you click on a point like right here, you can click on it. Usually, okay, for some reason, okay, it wants to click on that point for me. Okay, for some reason, it doesn't want to stay very long, and it doesn't want to work very well. All right, I guess it's not gonna do it for me very well, but 1/5 is 0.2. We can verify that in our calculator quickly. So just 1 divided by 5, that's 0.2. So -1/5 would be -0.2. So I'm just seeing what is the y coordinate. For one thing, I can just see, maybe if I scroll in a little bit more. If we scroll in here, we can see that this line is approaching a horizontal asymptote. See, as I go further and further out, and you can see that this is one hole right here. That's one hole. And there's 1, 2, 3, 4, 5. There's 5 sections in here. So this is 1/5. So as we go far to the towards negative infinity, as x gets larger, smaller and smaller towards negative infinity, notice that this graph is actually approaching -0.2. As we go further out here, if it'll click on it, if these things will work for me, then we can see that this graph is actually getting closer to 0.2. Yeah, this point -0.189 right there. And then look, it's getting -0.19, -0.9. And see how as we go further, and my graph, and I zoomed way out on accident. As we go further out here, it's just going to get closer and closer to this point, -0.2. So if we go way out, we can see that this graph is actually approaching -1/5, like we thought it was. Okay, so you can verify it on a graph, but as you can see at this moment, I'm having a really hard time getting the zoom right so you can actually see something in this graph. So anyways, and you can see as we go in the other direction, as x approaches positive infinity, let me see if we can go back in. You see it comes up from below and then it's approaching, again, it's approaching -1/5 in that direction as well. So we verified that that's what the graph actually does. Now let's look at the next equation, because in your notes, it says we need to find a long range behavior of 5/8x + 8. So we can graph that to see what happens in the tails. That's the long-term behavior. So I graph that equation. And you can see as x heads toward negative infinity, we are getting closer and closer to zero, the line 0. As if we go further out here, we keep going, you see how we're getting closer and closer to 0, the y coordinate is. Okay, as we go toward positive infinity, you can see that the graph is coming from the other direction, but it is getting closer and closer to 0 as well. As we travel further and further out here, 0.4, 0.35. As you can see, it's getting closer and closer to 0. Even if we went way out here, it's still not equal to 0 quite yet. So it's negative 1.11. And like I said, it's going to go to infinity. It's never going to quite hit 0. That's what a asymptote is, but it's getting closer and closer to 0 as we go further and further out there. So we were correct when we said that as x approaches positive infinity, the function actually is approaching 0, and as x approaches negative infinity, the function does in fact go to 0. Okay, let's also do this one. So I graphed this function. So what I'm showing you here again is that when you just graph the graph and you look at the tail ends of the function, that will tell you, you can see where the graph is going. And that'll answer the end, that'll tell you the end behavior of the function. So let's see what the final, this graph looks like. I believe it's x squared plus 1 over x cubed plus 1. So here it is. I'm going to go ahead and click its graph so we get to see it in green here. We go back to 0, 0, 0, 0. That's a problem with graphing these to find the end behavior, is that you don't know where to look in this graph generally. So unless you know about how to graph these yourself, you would not know where or which window to really look in. So that is a problem with this method. Okay, so as we go toward negative infinity, notice how it is actually approaching 0. And it never goes above 0, but it just approaches 0. We can see that by dragging this point this way, you're getting closer and closer to 0, a height of 0, right? Remember, we're focused when the limit is focused on the y coordinates or the height of the function and where the height of the function is going. As we go off toward positive infinity, the same thing, it's getting closer and closer to 0. As we go further out, we can see that it's 0.056, 0.05, and if we went way, way out here, it would be really close to 0 still, but it's not quite equal to 0. So we were correct when we said that this function, as you go toward positive infinity, is approaching 0, and as we approach negative infinity, it is also approaching 0. Now, I actually added a fourth problem in here. It's not actually on a practice test, but I meant to do a problem, and I did it again. I don't know why. Okay, I meant to do a problem where the numerator is actually larger than the denominator. The degree here, the numerator is larger than the denominator. So I'm going to graph this one and see what that looks like. Oh, and I graphed x cubed over x squared. Okay, let me just fix this. So let's see what this graph looks like. I think I already answered this question, and I already said in the practice test key, I already made answers for this question. So let's verify the answers by just graphing this graph. So now this graph is going to be in purple. and this one's hard. It kind of looks like a straight line. And as I zoom out further, it looks even more like just a straight line. So we can see that as we go toward positive infinity, if x goes to positive infinity, we're just going to continue getting larger and larger. So the y coordinate here is going to positive infinity. As we go higher and higher, you can see it's just going to build and get higher and higher. There is like really nothing it's approaching, it's just going toward positive infinity. And then as we go the other direction, as we go off to negative infinity, the number just gets larger and larger and negative as we go that way. Right? So as you can see, like where is it headed? It's headed to negative infinity. So we verified that actually when I graph that function, darn it, okay, the function as x goes to positive infinity, the function actually goes to positive infinity. We just saw that. And as x goes to negative infinity, the function actually goes to negative infinity. So that's why those are the answers. And we saw the graph to verify that answer. So in short, you can just graph these and see what was happening in the tails as we go far high, large negative numbers and to large positive numbers to judge what the long run behavior is of a function. I wanted to kind of explain, and it's probably a good idea if you kind of know a little bit about these functions, because like I said, it's hard to really zoom in on the graph and where like you said a minute ago, it's kind of hard to even find the graph if or find out which area you should really be looking at or where to zoom or how much to zoom or how much to zoom in or how much to zoom out. That can be challenging. So it's good for you to know some basic things about the graphs before you begin them. So here's some basic things. There's 3 cases for rational functions. There's a situation if the degree in the numerator is less than the degree in the denominator. That's what you have here, example. Let's see if I can find a annotation. Okay, yes, okay, sorry. See how, no, and I don't want to. See how the degree at the numerator here is less than the degree at the denominator. In that situation, then the graph it's going to be increasing a lot faster in the denominator than it is in the numerator. So imagine the numerator just staying the same and the denominator getting a lot bigger. Then you're going to get smaller and smaller fractions, and then you're going to go, the denominator is getting bigger, so you're going to go, it's going off towards 0, as you notice, just like 1 over x. And the values would be going off to 0. And what's happening is x cubed is a function that's getting so much bigger, so much faster than x squared is, that it's kind of acting as if it's like 1 over x. The top is sort of staying the same, like 1, and then the bottom is getting bigger, so that's why you're going towards 0. Okay? So if now the second case is if the degree of the numerator is equal to the degree of the denominator, then the graph will have a horizontal asymptote, but it'll be the ratio of the coefficients to the leading term, numerator to denominator. So you will have a horizontal asymptote. Oh. So see how they're both, the leading term of the numerator and denominator are both at to 2 second power, so the degree there is equal. So if if you just look at these, the ratio of the leading terms, which is the coefficient here and the coefficient here, this would be a 1, then that will be the horizontal asymptote. It'll be, oh, sorry, it's 2/1. And that is because this x squared is growing the same as the x squared in the numerator, but because there's a 2 in the numerator, it's going to grow twice as big. So that's why we're going to have a horizontal asymptote of 2/1. Okay, the last operation is that if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. And the end behavior will mimic the resulting function found taking the ratio of the leading terms. So here, the ratio of the leading term will be this one over this one. So it'll be x cubed over x. So that'll be x squared. So if we explore the end behavior of the equation x squared, then that would be the end behavior of this entire function. Okay, so if that can help you, now I want to just show you, I actually graphed my 3 examples here, and I showed you, and I also graphed the ratio that we use. So this is the graph, this rate. This right here is the graph of x squared plus 1 over x squared plus 3. So you can see that it's headed off towards 0 in both directions as we go to positive infinity here and as we go to negative infinity. But a faster way to see that than graphing, you could just look at the ratio of the leading terms and then simplify that and then graph the ratio of the leading terms, and you would quickly see that also the ratio of the leading terms, the graph of the ratio of the leading terms looks very similar to the graph, the actual graph. And this one 1/x, if we just memorize what that looks like, then it's not hard for us to automatically, from the ratio of the leading terms, to graph and find what the long-term behavior would be. So see how the long-term, however, notice that right here, there's a little bump that's different than the 1/x squared graph. But see how in the tails and the end behavior of both of those graphs are the same. So that's why it's convenient just to look at the ratio of the leading terms, because its end behavior is the same as this more complicated function. Okay, let's look at this one. I graphed the second case here, and the actual graph looks like this. You can see that it's heading toward, at the tails here, it's heading toward this +2 on both sides, just like we thought it would, because we said the horizontal asymptote would be 2/1 or just 2. If I just took the ratio of the leading terms, that would be 2, and it would give me a straight line of 2. And see how the end behavior of this straight line, y = 2, is the same as the end behavior of this more complicated equation. So that's why we can just rely on this ratio, because it has the same end behavior as the original, more complicated and harder to graph. Lastly, I graphed this big equation, and it actually looks like this. This is the actual graph here. You can see it's at x = 1, because that would make the denominator equal to 0. We actually have a vertical asymptote here. So if we just take the ratio of the leading terms here, that would be x squared, and that would be the graph of it. But notice that the in behavior of x squared is the same as the in behavior, because here's the in behavior here. Sorry. The in behavior is here, and the in behavior is here as we go to positive negative infinity in this direction as we go to negative infinity in this direction. Although, we see we have a vertical asymptote in there. That's not in the tails. That's kind of in the middle point. So we can kind of ignore that when we're looking for the long range behavior of the function. And we notice that when we're just looking at these in tails, it does match the in tails of the x squared function. So that's why we can just simplify our lives and just look at the ratio of the leading terms and look at what the entails of that function look like, because they're going to mimic the entails of this more complicated function. Interestingly enough, when you do have your degree in the numerator larger than the denominator, you can actually perform long division. And I have done it. Here's my long division, I believe. Yeah. So you could have actually done long division of so here's the polynomial long division. And we actually found out that this equation actually simplifies to be this. But I thought maybe the graph of this would look exactly like that. But of course I would be wrong, because the x minus 1 the bottom creates that vertical asymptote. So I actually graphed the answer that I got when I divided those two polynomials, and this was the answer. And I noticed that this answer actually is exactly the in behavior of this function. It's just the graph without that crazy vertical asymptote. So and then also you notice that we could perform the full long division here, and that would be kind of a lot of work. But when we do the ratio of the leading term, we are just focused on the first coefficient, the leading term of the answer when we do long division, which gives, if we just do a rough draft of the first leading term of the answer, which is what we do, which is what the ratio of the leading terms gives us, then that graph will match the actual in behavior graph. It gives us just a rough estimate, or not rough estimate, but it gives us a rough graph, but it's good enough to see what the in behavior is doing, because as you see, if I actually went through the hard work of this long division, the in behavior of that function is the same as just the ratio of the first terms. The equation that's resulting from the ratio of the first terms. So that's why it's easier for us just to use that ratio of the first terms rather than doing all of this long division. So I graphed here for you. This is the actual original rational function. And when I did that long division, I simplified this rational function to be this polynomial. And it's actually shown here in blue, but it actually overlaps part of the original function, and it's just overlapping the in behavior. So let me show you more directly. So you can see this function just goes right here and right here. Didn't mean to make it curly like that. So basically, it's just that quotient that I got, the answer in the division problem after I did the long division of that, it just looks like the in behavior of the original function. There's an added little blue part right there, but I just wanted to just point that out. It's kind of interesting. And but of course, we can simplify our lives rather than doing that long division. Like I said, we can just look at the coefficient of the leading terms, which gives us the leading term of that long division problem. And that's good enough for us to identify what the long-run behavior of this function would be. All right. I hope that you found this valuable. So when you're dealing with rational functions, it'll be very important for you to identify whether the numerator or denominator has the higher degree. And that'll really help you to determine whether there's what the horizontal asymptote is, or in the third case, whether there is not a horizontal asymptote. All right. Hope you found this video valuable. Have a great day.